Everybody, thank you for today's attendance for today's webinar. This is Steve Richter with Frontier Precision. I have on the line here today that's going to be doing the presentation. I have Matt Schwartz. He is in charge of all of our build construction, and he's going to be talking today about using the Trimble SX10 to capture as-built data. And we're going to try to leave this at about 30 minutes or so. We are recording this, so there will be a playback, and we will leave that or let you know when that is available since you are a registered attendee, so that you can share it with your colleagues or go back to it and view some of the content later. Everybody is in listen-only mode, so if you do have some questions, we encourage you to use the chat window. There is a chat window in your GoToWebinar interface on the right-hand side, and you can just type in your questions there, and we'll answer those at the end of today's session. With that, I'll turn it over to Matt, and Matt will run you through today's presentation. Thank you.
Okay, thank you, Steve. As Steve said, using SX10 to capture the as-built data on a construction site specifically is what we're going to kind of cover today. So we'll kind of start out. The agenda, we're going to kind of go over a common scenario that exists in many construction sites today. We're going to discuss the SX10 robotic total station, kind of go through the process of what I did on the actual site for the setup and importing of data and kind of how the workflow goes. And then we're actually going to do a hands-on with the data itself in the Trimble RealWorks program. So the actual products used, the SX10 scanning total station. We have the Trimble Access field software. Specifically, the data collector that I used was the UMA 2. And then we're going to be using the advanced plant version of Trimble RealWorks software for point cloud work. So kind of a common scenario that happens in a lot of construction sites today is that the pace of projects now makes it extremely difficult for companies to monitor and verify the installation of materials and things on the site, whether that is mass concrete or maybe underground piping or steel erection, whatever it is, whatever is getting placed on site, keeping up and verifying that everything is going according to design becomes a pretty difficult task. And typically what happens is that you recognize the problem when the next part of the process of the construction workflow actually tries to take place. So if you are trying to set steel on top of an anchor bolt, if the anchor bolts are positioned wrong, you typically don't find out until the steel doesn't fit. And when that happens, you're at a very difficult spot because now you're slowing down the construction process. Your schedule gets behind, everything kind of falls back, and you're at a standstill until the issue gets addressed. Typically, when a construction company tries to as-built, you're only able to get about 5 to 10% of the data on a project. So a very small amount, it's really more of a spot check thing of maybe just really critical items of, okay, did this go according to plan? Was this installed right? Was this done right? And you're having a lot of gaps in your data. I mean, 5 to 10% is not much. If we can address the problems early, figure them out, find where we're going to have issues, oftentimes we can make adjustments, whether it's ordering the steel differently with the bottom plate or moving a wall over or whatever you need to do before it significantly impacts the rest of the process, either in time or typically it's in time and money. So really about early identification to help save the job a significant amount of cost. Currently, the way that as-built data is collected is really one of two methods. It's going to be either a discrete point collection using a total station. Typically nowadays people are running robotics, but conventionals will do it too. and you have the layout personnel, and they're just clicking off measurements, sighting or actually just walking with the prism pole. Either way works, but you're doing a single discrete point at a time. The other option that people use is 3D laser scanning. And 3D laser scanning is great, but it typically, it comes with some issues on the logistics side. It's typically done by an office personnel. Field personnel typically don't have the experience or the laser scanning use to really accommodate and do the work in a good fashion. So the discrete point measurement, as I said, easy to do. You can do it with layout personnel. They're used to using their total stations. It's something that you can implement really, really quickly. But it's a fairly slow process because you're taking a point measurement every time, maybe every 10 seconds or so. And you're only getting the discrete point that you're measuring. So if there is a bow in a wall or something like that, you're going to have a significant amount of a gap in your data that you might not catch. Really, 3D laser scanning is the better solution. It provides a complete picture. You're getting more information, but there's traditionally an additional expense. You have some logistical issues, like I said, office personnel, if they're the ones doing the scanning. Are they on site that day? Are they on site when you need them? Is the equipment available when you need it to not impact the schedule and slow things down to gather information? If you catch an issue, hey, we want to do a laser scan because that doesn't quite seem right. Well, is that available to you? You don't always know if the scanner can be there, if that person can be there, so it kind of becomes difficult and complicated to implement the 3D scanning into workflows. So really, kind of the solution that fits it is going to be the Trimble SX10. The SX10 is at its base level a 1-second accuracy robotic total station. That really, it can be used traditionally. It's a normal system, but what Trimble has done that really kind of gives you the extra bang for the buck and what makes it such a remarkable instrument is some of these features listed here. Besides your 1-second extremely accurate robotic layout equipment, you also have a 1,400,000 points per minute laser scanner, a telephoto camera that will provide you 84 times magnification. So a traditional total station is going to be in the roughly 30 times magnification when you look through the telescope sight with the crosshairs to an object. You're usually 30 times magnification. With this SX10 and the telephoto zoom, you have the capability of doing an 84 time magnification, so significantly, almost 3 times better. You're going to be able to get the point that you actually are looking to measure. You're going to be able to, like I did in this project, and I'll cover in a little bit, sight to a target to do your resection. It increases your capability significantly when you're able to see further from one setup and know that what you're trying to measure you can visually see on your camera and or on your tablet using the camera and know what you're getting. And then the fourth thing that it does is imaging and collecting information. They always say a picture's worth 1,000 words. That's a big thing to be able to do. So the imaging part of the total station is significant. It's a useful feature. People should implement it and take advantage of what you have there. And really how this machine is different is that it provides all of these features into one package. So one system, you're ready to go. All that helps having it in one system. It's one machine to purchase. You don't have to have 2 separate pieces of equipment. One maybe you don't use quite as much, the other one you use more often. There's nothing else to learn. If you know how to use the SX10, you know how to use it for whatever feature you need to. Also, there's less maintenance. You don't need to have additional extended warranties, do additional maintenance packages on it, service. So it's just easier for a company to operate and have it simple with just one platform, one package. Along with that one machine, it's one software. So you have Trimble access for your layout, for your scanning job files, for your images that you collect. It's a single source, it's a single job file. There's no more, I don't quite know how to use that software because I haven't used it very often. It's all right there. So it's a big benefit. It saves you with your implementation of it by just one piece of equipment, and one user can do multiple tasks and get all the information. And kind of the other thing is that you don't need to have anything else on site. So that one machine, if I'm using it for layout equipment, and then I need to do some as-built scanning, I don't have to worry about possibly getting a machine from my yard or getting the laser scanner from a different project. It's ready to go. I had it on site this morning. I did my layout work. I know I can do my scanning with it right afterwards. So there's no additional costs there. Makes it extremely easy for the logistics side to keep things normal. One thing that I kind of want to highlight is what the machine is not. With the 1,400,000 points per minute scanning time, that's pretty good. But if you are looking to get extreme detail, quarter-inch accuracy on a very, very large, or quarter-inch spacing, excuse me, not accuracy, on a very large area, a traditional scanner like a Trimble TX8 that shoots 1 million points per second will cut down your scan time significantly. So you kind of want to be aware of right tool job. This SX10 is great because it's a multiple use tool that gives you a lot of functionality and a lot of flexibility, but you want to make sure that you're not trying to do a huge amount of laser scanning with really high detail on it, because you're going to increase the scan times to where it might be a little bit prohibitive for you. All right, so the SX10 workflow that I used for this example, or that you can use just period, is one of the benefits. You can do a traditional survey workflow. With a traditional 3D laser scanner, actually having the project control on site is a little bit difficult to do. With the SX10, you can do your resection, you can do your backsite, whatever you want, and you're in your project coordinates automatically. You get your residual results, it's all right there for you. When your machine is set up, as I just said, you have your scan data. It's right there in the exact same coordinate system, whether it is an assumed coordinate system of say 5,000, 3,000 for the building, or you're on, as we were, county coordinates. Whatever it is, your scan data is right there with you. So for this project, you can kind of see on the building at the top of the picture, there were 3 control targets that were set up, actually in the very upper leftmost part of that picture, and then the structure kind of makes a little bit of an L, and the second control point was in the leftmost corner of that's kind of just cut off from the image, leftmost corner at the top, and then the third control point that I used was in the rightmost corner on the top, on the image, just cut off by the concrete there and the floor above. So I did a resection to set up my machine, got my residuals, was happy with the results, and from there I was ready to go. If you wanted to use the SX10 for general layout equipment, everything is the same as usual. You do your normal workflows, you set your machine up, and you're ready to go. It operates as a total station, conventional prism pole, conventional prism, you're staking points and lines. If you need to do DR measurement, great thing about it, 600 meter range. You have an extremely long way that you can shoot with this machine and still get a reading. Paired with that with the 84 times magnification of our telephoto lens, it makes it extremely powerful for being able to take a DR measurement at a long distance. You know what you're shooting, you can see what you're shooting, and you can shoot that distance that you need to. So general layout, it's same deal, you're ready to go. with the imagery on it. This is a big thing. So this picture that we have here was actually taken by the overview camera of the SX10. So here, I hope you can see my cursor right now, is where one of the targets was. Over here, you can kind of see the bump out there, the left side of from the bump out. The peak is where the second target was. This is the overview. So not designed to give you a huge amount of detail. It's a coarse, wide angle, wide area picture. The SX10 has 4 different cameras available to you. The primary camera offers a much higher resolution. So we've got the overview that gives you your kind of big picture. You zoom in a little bit and you switch over to the primary. We get that higher resolution, better focusing, better color, better distinction between objects. From there, we've got the telephoto. I described it as magic stuff. This is where we really get our benefit. You're able to see, and I'll have an image here in a second, a very long way with this telephoto lens. It's good stuff. And then the last camera that we have available is the optical plummet. And in this case, it's a video plummet. It's downward facing. It allows you to take an image, but also to see the plummet position of the robot. So you can document it that, yes, I was indeed, if you're doing a traditional backside setup, I was indeed over this monument or my control point, and have that for verification, and then continue on with your backside reference. So here kind of illustrates the differences between the 3 cameras that really matter. The optical plummet one is kind of separate, but the overview, primary, and telephoto mounted in the telescope of the total station are the ones that you're going to use for your viewing, coloring as point clouds, collecting images, whatever it is. So the parking sign on the left-hand side of the screen kind of shows the overview camera. A little bit fuzzy, you can still make everything out, but the brickwork, especially in the back, is not real clear. The middle one shows the progression that you flip over to by going over to the primary camera. Much more clear. You can see if you look kind of compare the two. I mean, we're focused in at just the parking sign itself. You don't get any of the structures around. And we're getting a pretty good level of detail there. I mean, that's fairly impressive to be able to go from that overview down to the primary and get that. Now when we flip over to the telephoto, that's where things become really impressive. I mean, this is a fairly good distance that we are away in these 3 images, and you can see the fact that the parking sign there could need to be replaced. It doesn't, the P looks like it's starting to kind of drift off there in the top where the paint is maybe falling off, but you're having issues. But you can see that allows you to get extremely accurate and close with your measurements. If you need to take a photo of that, maybe it's a plate or an embed location from a extremely far distance away, or it's up in the air, rather than getting somebody into a bucket for a remote measurement, you're able to just do it from the ground and get your information and get a good image to provide for documentation for somebody else. So imagery is very helpful. So here I have a video. Hopefully it should come through for you. I'm gonna make sure we don't have any volume on. So this is the actual scanning process, and what happens in the scanning process is the total station looks like it's moving robotically, and it is. The beam gets fanned out into 16 different beams, and it kind of, if you want to think of it as a paintbrush, it paints back and forth. And with the operation of that is it keeps track of the horizontal angle as well, and it will scan multiple areas at, or it'll do multiple passes over a specific area. So with a traditional scanner, if you have things like vehicles or people moving through your scan, you tend to pick up a lot of things that you have to segment out, a lot of artifacts and kind of ghosting that you get. The SX10 is much less pronounced than the laser scans because you're doing an area multiple times. So oftentimes if an object comes through, you can still get the data that you need and not have as many artifacts or things that you need to segment out as you're looking through your scan data. So that kind of, that little clip there just kind of shows that's nothing really more fancy than that. It just moves up and down, moves back and forth. The scanning process is extremely easy and just a button click over. So what we're going to do now is kind of go, hopefully I can get this to work for us, the hands-on with the Trimble Access Data Collector.
So what I've got here is I've just got the map screen of Trimble Access. I'll escape out. You can see this is Trimble Access, nothing special. So those of you that are familiar with that software, this will be very familiar with you. You see the ghost image up at the top right. It actually flashes through the different total stations and GPS, including the SX10 now. So you see that image just appeared there. If I go ahead and go into the map screen, I have several scans on. I can kind of look at those and see that you can see I have the scans on from that day. There's multiple scans that were done. I can zoom in on the project if I wish, and you can see that there was 3 measurements taken to those targets. Those are the resected targets that were shot on the building. And you'll notice that as the scan was done, that building that was in that far away distance was also picked up in the scan. So the distance on the scanner, and Matt will show a little bit of that in RealWorks, is absolutely amazing. The resected point and the scan point, setup point was over here and over here in the center of the project. And this is a nice verification tool, and this is why we bring it up, that you can bring this up in Trimble Access before you leave the project. So a couple of things of note here. One is I can verify that things were captured before I leave. You'll notice that there are 4 scans, scan 1 through 4, that were performed over various periods of time. The longest scan took 11 minutes to give you an idea, and that was a 365-degree scan, so probably a horizontal band. I guess Matt would be able to say that for sure, but a larger scan. And it only took 11 minutes, so not very long. And the note that I want to give here is that all the data is registered and in its proper place. There's not one part of the scan over here and it's shifted, and the other part is over here and it's shifted and it has to be registered later. That isn't the case in this particular instance. All of our data is here. It's in a traditional survey workflow, and because of that, all the scan data is referenced to the same coordinate system, just like Matt said earlier. That's really important because if you look, we'll see in this job here that this was done with a scale factor of 1, but we could have done this job in a coordinate system of our choosing. So it could have been in state plane and scaled to ground. It could have been in a county coordinate system. UTM doesn't matter. So that's pretty important to note because there's really not a lot of scanners out there that can perform operations like that, especially combining the total station measurements. And even since you're running Trimble Access, honestly, GNSS measurements to the same project. So we'll go ahead and I'll see if I can get this to zoom in on some 3D. Maybe not. Try that again. Zoom in on this particular area here, maybe just to give you an idea what we're looking at in Trimble Access. You can see some of the floor I'm looking at top down. So you can see some of the floor was captured. If I zoom out here, you can see we actually got some stuff at pretty long distances. And when we bring this into Trimble RealWorks in just a moment, Matt will maybe show a little bit more of that. But this is just to give you an idea that we are a traditional survey workflow. Nothing's changed. If you're familiar with Trimble Access, the workflow is going to be very familiar to you. And the total station measurements are geo-referenced and combined with the scan data right here in the field. Is there anything else you wanted to point out in Trimble Access before we shift over to the software?
Yeah, so kind of to recap a little bit of the scan thing real quick. That largest scan at 11 minutes was a full dome, fairly coarse, so not a lot of density, but you can see from the information that we're we're capturing, it's still extremely informational with the picture. So we have that, and then what I did with the different breakups, why there are 4, one full dome, and then I focused in on the areas. So that's kind of what I wanted to highlight with the workflow is, number one, I wanted to keep the data set fairly small, and you'll see that when we get into RealWorks here. But number two, you're able to pick what you need to gather the information and then just scan that area. We can't go through the actual process right now on the screen for you of what buttons to click or how to work, but you use the overview camera and you're able to fence in an area if you want to, which is what I did for one of the scans, actually 2 of them, excuse me, and one of the ceilings and then just kind of one of the areas. And it's an extremely easy interface for gathering and starting your scans and picking out what you want to do. So, I mean, the learning curve is virtually non-existent. You pick what you want, you do that. You don't have to worry about having, with the traditional million points like a TX8, of capturing a lot of irrelevant information where your file size still gets large. The SX10 will allow you to keep it very concise, very clear, and just get what you need. So, very nice feature with that. With Trimble RealWorks, it is similar. There might be a lot of you out there, excuse me, using the TBC program, Trimble Business Center. You need the scanning module to be able to use this scan data, obviously. But all you have to do is just go ahead and drop in your job file and your folder. So what happens, the scan files actually get stored in the job folder on your data collector, and they're already organized. And if you bring in the job file as well, that was this file right here, along with that, it kind of comes as a package, and it imports in what you see right here. There is no registration for the 4 individual scans like you traditionally get. You are ready to go. Because I didn't have elevation on the control points, it wasn't given to me because the construction companies weren't doing it. There's not the actual 5001, 5002, 5003 points that I use for the measurement. If they were there, they would be right up here. So this would be 5001 right here, 5002 would be right over here, and 5003 would be on this building, or on this corner of the building right there. Now you can see here that we've got neighboring structures, significant amount of information. I mean, this building over was 2 blocks away, and I mean, this was a coarse scan. So this is the very roughest amount of data and density that we can get out of the SX10, and still there's a reasonable amount of information to pick up exactly where window openings are. If I would have wanted to, I could have done a scan and fenced in this area and got a much higher density there. What I do kind of want to highlight is that from this one scan here, keep zooming out, it might be a little tough for some of your screens to pick up, but there is some data way over here. And this bar right here is 800 feet for reference. With Trimble RealWorks program, you're able to do measurements between points. So I'm going to come in and I'm just going to do a distance measurement. So you'll see over here it says pick 2 points in the corner. And I'm going to tap over here. And I'm going to tap roughly where I was for there. 1,700 feet. Pretty impressive. I'm just going to turn my volume down. So pretty good, but there's actually some more data way back over here too. And that data is 2,800, almost 2,900 feet away. So that SX10 in one coarse scan was actually able to get measurements. Frankly, it was so far away across the river, I'm not even sure what it captured, but it has data at 2,900 feet away. So very, very impressive EDM that came out of that. All right, so what we're going to do is kind of get back into more of the relevant information. So I told you I was going to keep the data sets fairly small, and that's kind of what I did here. We don't have a whole lot of information. The structure is a new high-rise condo complex in downtown Minneapolis. It's going to be 17 stories here and 12 stories here. It kind of runs vertical here. And if I get into kind of the view here of where the actual scanner is, so here's the overview image that I took, so you can see that we have colorized information here. If I was to do a full dome image, we'd be able to see that as well, but I don't want to get too crazy with it. Here's the actual information of the actual scan. So the full dome, so density for this area was not real significant. But you can see that I highlighted this area here up above and down below. So this was one of the scans. Another one of them was up this area here, and then this was the third where you have more detail. So here's a shoring you can see on the post-tension slab. What we kind of want to look at, or what this allows you to do, as I've already said, get the information you want. We're going to look at this area down here for floor flatness. We're going to look at this area up here for flatness of the ceiling. And then this core right here, this core wall, this is going to be the elevator shaft for verticality. Now what I'm going to do real quick as well is just kind of show, I already did the one measurement, but just by doing this scan, if I wanted to verify information just for measurements and kind of just hey, where are we at on this? How well are we doing so far? What's my spacing between these two columns here? It's basically 28 feet. So I can go through and anywhere I have point information, whether it's back there or it is up here, again, 28 feet, we're okay, we can keep on. So if I want to measure, same thing with if I do vertical, ceiling heights, 14, a little bit different there. I can just pick off. So 20 minutes of scanning, and now I am now able to use the data that I have in a lot of different ways. This is a snapshot. I want to come back to it in a week, I can. We've got the capabilities. So let's kind of, before we get too long over time, go through. RealWorks software has an option inside of it for floor flatness. So I want to verify that this area right here is good. I can use a segmentation tool and actually cut out an area. And just have it grab this stuff right in here. I've already done so over here, kind of cheated and got ready ahead of time. So I'm not going to create that, but I'll go ahead and turn off the pull point cloud and just turn on the floor area. So here it's kind of parsed down a little bit. You can see we've got the, I'm going to go ahead and flip our view back so I can get back into. Here's my view, top-down, orientated on a north and east coordinate system. So if I want to come in, view floor flatness report, I come into floor flatness inspection. Going to turn the whole point cloud off. Oh, excuse me. Going to define my area that I want to inspect. In this case, it's this part right here. Done with that. So now I have my grid origin point, which is automatically selected, and notice that this is in a county coordinate system. I don't have any accurate elevation information tied to it. I could have hit a benchmark and done that, but I didn't for this project have any benchmarks out. I'm going to do a grid spacing of every foot, or excuse me, every 6 inches. If I wanted to change that to 1 foot, I can. You can see that the size of the grid squares change. And then what I can do, if I have a elevation benchmark out there, I can physically come in and I can pick exactly where I want it to be. If it was right here or over here, wherever it is. Or what I'm actually going to do for this is just do an average elevation for my floor. So it's going to compare this to the average, and I want to know everything within 0.02 feet or a quarter inch when I click preview. So now I have my report. Looks kind of crummy right now with the extra line work and everything, so I'm going to go ahead and turn off the grid because I don't care about that. And I don't care about looking at the point cloud because I've got my coloring. Turn that off too. So what you see here now is everything in blue is actually below grade a little bit of the 0.00 or 0.77 elevation, and everything in red is above. So I can come through and I can look through. Having the scan information is important because I know that there was a cart right here and I didn't quite parse down all the way, so it's just telling me, hey, I got some of the wheels on the cart. There may have been some other objects over here and here that caused it to be high a little bit, but you're able to very quickly get a report of how is my floor doing? Where am I at? I can tell you that this is a condo complex, so they are going to have to do something like this on this project to make sure, because if you're putting hardwood over the top of a, we'll say $400,000 condo, you cannot have that buckling on them in a year. We can create a report, we can get elevation information, we can get volume information. So I actually have already saved that and created it. Just to kind of go through that real quick, we get a map. So here's the actual report that gets created. Oh. I'm going to use so here we have grid spacing. This I did it at a 6-inch grid spacing before. Here are my volumes, total areas. This is a pretty small area. Here's my square footage above and below, and then I have a contour map here. If I want to look at the map as well with annotated deviations, I can come in and notice that there's little crosshairs everywhere. This is greater than the quarter inch or 0.02 tolerance that I allowed, so it came up with red. You can see now with this is probably a hose on the ground. So where am I going to have an issue? Well, actually, you know what, this whole area here, this probably wasn't the actual object or anything in the way. This is just a high spot in the floor. Same thing with over here. This isn't anything other than just a depression in the floor. So these areas are going to have to be addressed. Same thing with this spot over here. So you can see, you get point information. You also get a actual points file that you can then load into your data collector and stake out. So the floor flatness tool is extremely powerful, extremely helpful for being able to document very quickly and easily the floor flatness. Next thing that I'm going to talk about is going to be coming in and getting the elevation of the ceiling right here. So I want to know how flat and how well is this ceiling poured right here. With the software, I can come through and create what's called a limit box. And then simply drag to what I want to be illustrated. See, maybe I don't want this much, so I can go through. I've already got those kind of predetermined. That's how I created that one, and then this actual point cloud information. So this is the surface we're going to use for our next example here. How well and how flat is this object? So I can come in and I can come into model and I can use the CloudBased Modeler. And what it allows me to do is segment out an area, which I already did with this area here, and then create several different geometries. The one in particular that I looked for was plane. And once I do that, I have the opportunity to create a geometry, in this case that plane, fitted to this point cloud. So it's going to go through and it's going to create a plane with the best fit, so a flat plane, to this actual point cloud here. So what I'll do then, that was created right down here where it says ceiling plane fitted. I can come into the inspection tool again, and I'm going to come in, close out of here. I'm going to take the ceiling area, and I'm going to take the ceiling plane, and I'm going to do a surface to model inspection. So I have a surface and I have a plane that was created. And what will happen is that, kind of like with the floor flatness tool where I get a color map, it's giving me that the floor is kind of leaning over towards this way as we move. So you have very quickly, very easily a tool for doing the comparison of point cloud data, if there's any humps or dips in the floor, and then you create the plane from the model information, and then compare the two, the model and your flat plane, and you know exactly what's going on with your surfaces there. And the next thing or final thing that we're going to kind of talk about is going to be the core wall. So what we have here, where are we? Okay, so this wall right here, I already kind of touched on that this is the elevator core for the building. How do we know that this is going to verify, or that this is verified going straight up and doesn't have some type of a bulge to it, or that it is truly going plumb? A lot of these things are slip formed or lift and slip when they're installed. So concrete gets poured into molds and then cures, and then they lift the whole apparatus up. If that doesn't go up true, you're going to have an issue with your structure at some point. So how do we actually measure? With the 3D laser scanner, we can hit the scan. We can segment out the information that we need to. In this case, I've done that here. So I'm going to isolate just this wall. If I really wanted a lot more information, I could, but the density on here is fairly decent. I can pull measurements just like we're used to. So it's telling me this is 14 feet high. I haven't shown you this yet, but along with the measurement tool, if I grab on a point, it will give me the coordinate for that point. So here we're 9 feet in elevation above what the machine called 0, and here is my real world coordinate for that exact point on the wall. So if I want to export out some points, I can select them, get those measurements, create a list, use that. We'll just kind of come back in, last thing, core wall, and then I have a core plane. So this time it's vertical. Again, same exact tool, surface to model inspection. So here's my actual plane that was fit through, and then I can do preview, and I can see that we have a little bit of waviness to the wall. There's some high spots here, and then there's some low spots back there. That could be because of my point cloud information, but I'm going to say that the wall just might be tilting back in that corner. So on a vertical plane, we're still able to capture this information. All right, so it looks like we ran over a little bit on time. I apologize for that, but I'll look through, see if we have any questions or anything. I'm not really seeing anything in the chat.
I see a couple here on my side.
We'll kind of open that up. Does anybody have any?
Matt, I see a couple on my side. Can you hear me there? One is on TBC. Can I dump this data into Trimble Business Center? And the answer is yes. I mean, it acts just the same in TBC. Some of the features that Matt showed, like the floor flatness, and some of those inspection tools aren't in TBC, but certainly it does support the total station robotic data as well as the scan data. The last question I have is the size of the files. So how big are these scans? So the size of the files, and that is just a function of all the data that's together. If I open up this project, I see all the scans, the photos that were taken, as well as the job file is 218 megabytes. So it's pretty small. And I do want to kind of accentuate on one of the features that Matt was pointing out on that band scanning. When you choose a higher resolution and you want that band scanning to go back over the project several times, and when it does that, it changes the horizontal angle slightly. What we've noticed that we didn't anticipate over a traditional scanner is that with that band scanning, it tends to pick up edges and corners a lot better than a traditional scanner because it's actually going over it multiple times. Not only the idea of somebody walking by the scanner and you happen to miss something that was important, the band scanning will obviously pick that up because it's going over it when the person is not walking anymore because there's a delay in time. But it also picks up those corners on those edges a lot better. So that's also something that we've noticed. But without trying to overrun this for more than 20 minutes here, we're going to go ahead and end today's session. I do appreciate everybody attending. Like we said, we are going to make this recording available in a few days, and we'll send a notification out for all of you that have registered. But again, thank you for attending today's webinar on the Trimble SX10 and AsBuilt data, and hope to see you at one of our future webinars. Thank you.